Have you ever sat on a plane, buckled in, and just wondered what really goes into making a flight safe? It's way more than just the engines and the wings. It's this constant, unseen battle with invisible forces, challenges that pilots have to calculate and conquer every single time. So today, let's pull back the curtain and look at the hidden science that gets you from A to B.
It seems totally backwards, right? The sky is clear, not a cloud in sight, perfect weather, and yet flights are getting delayed or even canceled. Why? Well, the answer is hiding in plain sight, in the air itself. It all comes down to a calculation that every single pilot has to get 100% right.
So how do pilots deal with all these invisible challenges? Well, it's definitely not guesswork. They have what you could call a secret playbook, a guide that is absolutely mandatory, and it turns all of these invisible, abstract problems into cold, hard numbers. And this is it, the Pilot's Operating Handbook, or POH for short. Now, this isn't just some helpful user manual you'd find in a glove box. It's the law. Inside are all the charts, tables, and data a pilot needs to figure out exactly how their specific aircraft is going to perform on that specific day under those specific conditions. It's the key to making sure a flight is not just possible, but safe.
You know, every single calculation in that book really boils down to just these three things. 1, how heavy is the plane? 2, what's the atmosphere actually doing today? And 3, what's the runway like? Getting the relationship between these three factors right, well, that's the heart of a pilot's job before they even think about pushing the throttle.
Now, of those three, the most powerful, the most unpredictable, is the atmosphere. And the best way to think about it is this. On some days, that airplane isn't just taking off from an airport, it's actually trying to climb an invisible mountain.
To even begin to understand this invisible mountain, pilots can't just look at the airport's elevation sign. No, they have to start with something called pressure altitude. Think of it like a standardized level playing field for the atmosphere. It's a baseline that lets every pilot start their calculations from the same theoretical point, no matter what the local weather is doing.
And this is the big one, density altitude. If pressure altitude is the baseline, density altitude is the reality. It's the feels-like altitude for the airplane. It takes that standard altitude and then adjusts it for what the temperature is actually doing. And here's the key. Hot air is thin air. And thin air makes the plane perform as if it's at a much, much higher altitude than it really is.
Flight manuals are incredibly clear about this, and it's a mind-bending concept. It says the plane will perform as if it's flying at the density altitude, no matter where it actually is. So you could be sitting on a runway that's at sea level, but on a really hot day, your plane's engine, propellers, and wings will perform as if they're already thousands of feet up a mountain where the air is thin and weak.
So, what are the villains that create this thin air, this high-density altitude? Well, it's this trio. High elevation, that's the obvious one, but high temperature and even high humidity are just as bad. All three of them work together to reduce the density of the air, basically robbing the aircraft of the performance it desperately needs to fly.
And the consequences of this thin air are massive. I mean, it hits everything. The engine gets less oxygen, so it produces less power. The propeller has less air to grab onto, to bite into, so it creates less thrust. And the wings have fewer air molecules flowing over them, which means they generate less lift. All three critical ingredients for flight are seriously degraded.
Okay, so let's see how all this theory gets put into practice in the first critical moment of any flight, the takeoff. This isn't just a matter of hitting the gas. It is a very precise, high-stakes calculation.
One of the biggest wildcards here is the wind. A headwind, wind coming at the plane, is a pilot's absolute best friend on takeoff. It's like getting a free boost of airspeed, helping the plane lift off the ground in a much shorter distance. A tailwind, though, that's the enemy. It's pushing the plane from behind, forcing it to roll down the runway for a dangerously long time.
And this is where the physics gets really unforgiving. So let's say a pilot thinks, I'll add a little extra speed just to be safe. They decide to take off just 10% faster than the handbook says they need to. Sounds like a good conservative idea, right? But what does that little 10% change actually do?
It's a terrible idea. Because of the laws of aerodynamics, that tiny 10% increase in speed demands a jaw-dropping 21% more runway to get airborne. It's not a one-to-one relationship at all. It just goes to show you how razor-thin the margins are between a safe takeoff and literally running out of pavement.
Of course, getting off the ground is only half the story.
Landing brings all those same invisible forces back into play, but this time they're creating a whole new set of challenges and risks for the pilot. When you see a wet runway, your first thought is probably about skidding, right? Like in a car on an icy road. But for a heavy, fast-moving aircraft, there's a much bigger danger lurking on that wet surface: hydroplaning. Hydroplaning is when the tires are moving so fast they literally start to surf on a thin film of water. They completely disconnect from the pavement. And when that happens, forget about it. Brakes are useless, steering is gone, the pilot is no longer in control, they're basically a passenger on a multi-ton toboggan.
But this isn't totally random. Pilots can actually calculate the exact speed where hydroplaning becomes a serious risk, and they use this surprisingly simple formula. It's just 9 times the square root of the tire pressure.
So, let's make that real. For a smaller plane with a pretty typical tire pressure of 36 psi, you run the numbers and it tells you that this terrifying loss of control can start at just 54 knots. To put that in perspective, that's about 62 miles per hour, a speed the plane is well above the instant its wheels touch down. This is exactly why hitting the target landing speed is so critical. And look at this, the margins for error are just as brutal on landing as they are on takeoff. A pilot coming in just 10% too fast needs 21% more runway to stop. And a 10-knot tailwind, something totally outside the pilot's control, has the exact same dangerous effect. 2 completely different problems, one pilot-controlled, one environmental, both causing the same massive increase in risk. Okay, so we've gone through all this technical stuff, but why does any of it really matter to you, the passenger? Well, because understanding this completely changes how you look at the experience of flying. Remember that hot summer day from the beginning? That frustrating delay while you're sitting on the tarmac? It's not an inconvenience. That's your pilot, with that POH in their lap, recalculating everything for that high-density altitude, for that invisible mountain. They might be waiting for the temperature to drop just a few degrees or for the wind to shift to make absolutely sure your takeoff is safe, not just on time. And make no mistake, the stakes here could not be higher. This is a genuinely sobering fact from the FAA. The landing phase is responsible for more pilot-caused accidents than any other single part of a flight. So mastering these invisible forces isn't just about being a good pilot. It's about life and death. So, the next time you're on a flight and you feel those wheels lift off the runway or gently touch back down, just think about that complex dance of weight, atmosphere, and physics that's being conducted up in the cockpit. Your pilot is climbing an invisible mountain, and they've calculated every single step to get you there and back safely.